Welcome to the third video of my model storage robot project. In this video I'll talk about the interface between the storage robot and the remaining components of the project. To reiterate, here is the big picture I developed in the first video of this series. If you haven't watched the introductory video yet, I'd strongly recommend it. In the previous video I explained the hardware components that make up the storage robot. In this video I'll be focusing on the interface between the hardware and the Photon. It's important to get a number of aspects sorted out before starting to program either side of the interface. There are a lot of aspects to think about when designing an interface, especially for professional system design. Fortunately, in this project, I'm not aiming for the levels of robustness, versatility and reliability required in a professional environment. This is a hobby project, so I get to choose which problems I want to tackle and which I can ignore. One of the first decisions when designing an interface is, do we want to build a serial or a parallel interface? For serial communication, you break up the data you want to transmit into individual bits and transport the bits sequentially through a single connection. That's usually done with the help of a specialized chip, usually called a UART, for Universal Asynchronous Receiver Transmitter, although many UARTs also support synchronous communication depending on the protocol implemented. For parallel communication, you've got a single dedicated connection for each bit you want to transmit. Let's take a look at some examples. When you plug in a mouse, it's likely to be a USB device. USB is Universal Serial Bus, the serial is in the name. For your monitor, you'll use HDMI and other digital video connectors, which are serial connections as well. So is FireWire. Moving on to internal components. If you plug in a new graphics card into your PC, you'll probably be using a PCI Express slot, which consists of multiple serial communication channels. For your newer and bigger hard drive, you'll probably use SATA, serial ATA, which again has serial in its name. To connect multiple computers, you may want to use an Ethernet network, which again is a serial communication. It appears that parallel communication has almost completely disappeared from the current technology market. Here's an example some of you might remember, a legacy printer cable, and you can see why they have disappeared. You need huge connectors because of the large number of pins, and you need expensive and bulky cables. Now it looks like serial communication might be the way to go. However, there's a slight problem for this project. The Robo Interface does not have a UART that we could use from the Robo programming environment, and you really wouldn't want to construct a UART in flow diagrams. However, we've got several I/O lines still unused, so for this project, parallel is it. The next thing we need to determine is the topology and the roles in the communication. In our case, it will always be an end-to-end connection between exactly one Robo Interface and exactly one Photon, which simplifies things a lot. Here's an informal example of how a communication between these devices might look like. The Photon asks, "Do you have a piece in your input area?" To which the robot responds with, "Yes, I do." The Photon then tells the robot to pick up the piece, and after that has been done, tells it to identify its color. After it learns that the new piece is red, it tells the robot to store it in a certain location. This is an example of a so-called master-slave communication. The Photon is always the initiator, sending a command, and the Robo Interface replies with either an acknowledgement or, depending on the command, the information requested. So what are the commands? Which arguments have to be supplied by the Photon, and what responses can be expected from the robot? The first basic command is to initialize and recalibrate the robot. We might need to do that from time to time or after some unexpected event occurred. This command does not require any arguments and does not produce a result. The next command would be to check the input slot using the photoelectric sensor, to which the robot responds with empty or occupied. Then we can tell the robot to pick up a piece from the input slot, which should normally yield OK as a result. However, if something goes wrong or we forgot to check the input beforehand, the robot might also tell us, "I haven't picked up anything." Usually, we would then tell the robot to check the color of the piece it is currently holding, yielding either empty or one of the three colors of the pieces. Then we can tell the robot to navigate to one of the storage bins, identified by their column A to E and their row 1 to 4, and store the piece. Similarly, we can tell the robot to retrieve a piece, which again should yield OK as a response, but occasionally might also yield "I haven't picked up anything." Finally, we can tell the robot to drop the piece it is currently holding into one of its 6 output slots. Since we've already decided to implement a parallel interface, We now need to determine the number of bits or lines to encode the commands, arguments and response values. Let's take a look at the responses first. The commands yield either no result, one of 2 or one of 4 possible values. Since we've got at most 4 values to encode, we'll look that up in our trusty table of the powers of 2. 4 is 2 to the power of 2, so we need 2 bits to encode the response values. Similarly, we've got 8 distinct commands. So when we look that up, 8 is 2 to the power of 3, so we need 3 bits to encode the commands. Fine so far, let's move on to the arguments. For the x position, we have to encode 5 values, so 2 bits are not enough, we need 3 bits. For the y position, with 4 values, 2 bits are sufficient. For the output slot z, we need 3 bits, but since x, y and z are never transmitted together, we can reuse the same lines. This means that we need a total of 5 bits for the command arguments. Combined with the 3 command bits, we need a total of 8 lines going into the Robo Interface, and we'll also need some additional transmission control lines we'll talk about later on. Sounds good, but taking a closer look at the hardware, after the construction only 7 lines are left that can be used, so we need to come up with a different design. A first approach might be to transmit command and argument serially. In this example, we first send the navb command, followed by the x position b and the y position 3. Similarly for the output, first send the drop command, then the output slot c. You can already see that we've got a variable number of arguments to be transmitted depending on the command, and some commands don't take arguments at all. In the common programming languages, that wouldn't be a problem at all, but here's our little spoil spot again. Handling variable length command sequences is surprisingly difficult in a graphical programming environment like RoboPro, so that's a road I'd rather not take. Do we have a better option? Yes, we do. For this, we'll first change the addressing mode of the navb command, combining x and y to a single ID ranging from A1 to E4. This specifies the command in a 5x4 matrix, resulting in 20 possible variations of the navb command. To encode this, we need 5 bits again, so apparently we haven't gained anything. However, 5 bits encode up to 32 values. For the variations of navb, we'd only use 20 command codes, so we've got 12 left. To encode the 6 variations of drop, we need another 6 codes, and the remaining 6 commands do not take arguments and so require 1 code each. In total, we need 32 combined command and argument codes to represent every action we could order, so we don't actually need more than 5 bits. This is the revised command table containing the commands we've already seen earlier, their binary representation, which will be handy in the next video, as well as the detailed specification of the response values. The order of the commands is more or less random. For instance, you can see that the input check was added later on. I mentioned earlier that we need an additional transmission control or handshake lines. Why? There are 2 additional requirements that we haven't taken into consideration so far. First, the Photon needs to know about the current state of the robot. More precisely, it needs to know whether the robot is able to receive and execute the next command. The second issue is a bit more subtle. The data and command lines might be set individually. There is no guarantee that they'll all change levels at exactly the same time, nor will they change levels instantaneously. There might be a transition phase where the levels are in an undefined range. Without a clear signal, the robot might try to interpret some nonsensical intermediate state as command and execute that. In our case, that would be particularly bad because the command codes don't contain a checksum, so every possible value is a legal command. So what exactly is the additional information that we need to exchange? The robot needs to have a way of telling the Photon, I'm currently busy and can't accept new commands. Please wait until I've completed whatever I'm currently doing. After that has been done and a new command is encoded, the Photon needs to tell the robot that the command is now ready to be executed, and after the robot has read the command, it needs to acknowledge it so that the Photon knows that the robot has received the command. To explain this in communication in detail, we'll use a so-called timing diagram. On the left-hand side, you can see the bits or data lines. These are the 5 command bits from the Photon to the robot and the ready signal, and these are the lines from the robot back to the Photon. The result lines were originally intended to transmit a color value and are therefore still called col0 and col1. Note that the busy is a low active or inverse line, hence the horizontal line above its name. That means that the robot signals that it's busy by pulling this line down to logical 0. We'll see why that is useful in a moment. In a timing diagram, the time progresses from left to right. Initially, the robot is switched off, so the busy line is low, signaling that the robot is busy. Well, not exactly. It's off. But the consequence as far as the photon is concerned is the same. The robot is not ready to receive the next command. When we switch the robot on, it performs its initialization routine, which might take some time. During that time, it still stays busy. When it's done initializing itself, it raises the busy line to logical 1, signaling it's ready to accept commands. It now waits and keeps waiting until something happens. That might take some time. When the photon relays an incoming command, it first sets the command lines in any order. Since the ready line is still low, this is allowed. Only after the photon is finished encoding the command, it raises the ready line, signaling there's a command waiting to be executed. The ready line is also a promise to keep the command bit stable until the ready is turned off again. The robot now reads and interprets the command bits and then raises its acknowledge line to signal it has read and buffered the command code and is ready to execute the command. This causes the photon to drop its ready signal, at which point the robot can no longer rely on the command bits being stable. Then the robot drops its acknowledge and busy lines, signaling it's executing the command. For the most part, that involves mechanical action, so that may take some time. If the command yields a result, the robot will then set the col bits and then raise the busy signal. Remember, the signal is low active, so that means I'm no longer busy. That signal is also a promise to keep the col bits stable for readout. After that, the cycle repeats whenever the next command is issued. To summarize, we've got the basic layout specified as an end-to-end communication with the photon in the master role and the Robo Interface as a slave device, and we'll use a parallel interface. The command set consists of 32 command codes that include the argument values. We need 5+1 bits to transmit commands to the Robo Interface and 2+2 bits to transmit the results to the photon. We'll be using an asynchronous communication protocol, so no clock signal, with 3 transmission control lines following the timing diagram that we've just seen. That means we're good to go. In the next video, I'll describe the implementation of the hardware control software using RoboPro. If you're interested in the progress of this project, there are a couple of ways to keep up to date. I have created a YouTube playlist you might want to follow, but of course you're also welcome to follow my entire YouTube channel. I'll also be blogging about this on the SAP Community Network, SCN. The link is in the description. You'll find the articles in my personal blog as well. If you have any questions, suggestions, or would like to leave any other kind of comment, feel free to use any of these channels to get in touch. I'm looking forward to it. Thank you for watching and have a nice day.